Okay, so tutorial number 3 will be tomorrow, Thursday, in person. I don't think the snowstorm will be such that we're going to close the campus again, so I'll be there in person. Okay, I'll see you there. So tomorrow there will be 2 things I want to talk about. We definitely have to cover part 2 about dynamic array. So from your tutorial number 2 last Thursday, you were supposed to study the constant increments, right? The amortized analysis for constant increment. Please make sure you do it before tomorrow. Otherwise, you can easily get lost tomorrow. So I'm going to continue with another strategy for the dynamic array, which is called doubling. That one is the more practical one because it turned out that one asymptotically, the average running time is going to be lower. We'll see tomorrow. And then hopefully we'll get some time left. I do want to get you started about how to implement binary search tree in Java. So in the lectures, I'm mainly going to focus on more like a conceptual, visual, theoretical part for the binary search tree, especially some mathematical properties. But I think since your programming tests, your assignment number 1 is coming up, right? So I think it will be something about manipulating tree in Java. That's something I want to make sure is you actually get both the theoretical part and also practical part. Okay, so I'll get you hopefully started, some gentle start, just about understanding the given code and also some JUnit test cases as well. So for those of you who may actually want to look at the materials for tomorrow, I'll really encourage you to do that. So you can go to the lecture site right here. Okay. So you will see under tutorials over here, tutorial number 3. All right. So these are, I posted all the materials, including the Java solution. But I would say maybe don't look at the solution just yet. Download the starter into Eclipse and also try it out. So there are only about 2 or 3 methods you have to implement. I don't recall the exact number. Not many. I think at least get back to the feel about generics and also how to manipulate the binary tree. Okay. So we don't really work on general tree, but just binary tree. You got left and right children. Okay. So you will see instructions already there, notes templates already there, starter, annotated notes. I'll post it tomorrow. Also recording as well. Okay. So for task number 2, this will be sound like a comparison of the 2 strategies. It's one of the tasks. So I can briefly talk about it tomorrow, but the detail is already there. You can also take a look later. That one's not in a rush. And this may be something you want to look at the final, the last, right? That's the solution to the task. All right? That's for the tutorial tomorrow. Everything is set. Right? Just come prepared. I think you'll gain the most. Any questions? Everything's good? Okay, let's do a quick recap from last time. And we're going to continue. Okay. So last time, of course, we spent a good amount of time talking about sorting orders, right? You got 4 different possibilities. Of course, the example we spoke about, selection sort, insertion sort, is only this case right here. But if I somehow modify, the sorting order slightly, you ought to know how to really, implement things, accordingly. Running time may not change, but you got to know how to make sure the algorithm is still correct if I change the sorting order. And selection sort, insertion sort, we just try to show to you that even if you're not given the Java implementation, you can still actually figure out the running time, by considering the critical steps, right? You can either try to visualize it, or you can try to be a little bit more precise and textual. You can actually figure out a table right here and then add up the running time. Okay, that's something you can do too. You got different flavor. And of course, the most precise way will be to look at almost like a running Java code or code in some programming language. And then you can actually figure out the pattern for the loop counter, right, etc. Right? That's something we also did last time. You can also take a look at maybe for insertion sort as well. That one there, even though you got a while loop, but it shouldn't be too difficult. You just have to make sure you still try to observe the pattern for the loop counter and see how to go from there. And then we talk about linear versus nonlinear. Of course, in this course, we're gonna do review on the trees for the coming few lectures, and we're definitely gonna look at graph very intensively for sure, or extensively as well. Okay, both the graph and the tree, they are nonlinear because it's simply not a case that you got unique successor and predecessor. Right? That's something we try to connect with what you learned in 2101 as well. And we talk about just review the terminology about tree. Number 1, it's very important to know whenever you got any node, the path from the node itself all the way up to the tree of the root of the tree It's called the ancestor path, right? It's a very important concept. We're going to use it when we actually do the tree rotations, possibly next week, okay? And then we spoke about these two important definitions, depth and also heights. As part of the tutorial exercise, I didn't include how you can compute recursively, usually, the depth and the heights. So depth should be for a node, and height should be for a tree, right? So that's something we could have distinguished last time. So if given those tasks, can you implement them in Java as well? I didn't quite include them in the tutorial, but I kind of hinted that you should really try them out as well. That's more like a 2101 review exercise. Make sure you can do them too, okay? All right, so we talk about given the depth of a particular node, you can see for all the nodes of a particular depth, you can categorize them as level something. So when we categorize in level 0, 1, 2, 3, the numbers here simply correspond to the depth for all the nodes in that particular level. You will see another diagram on the slides, slide number 5, all right, right here, okay, that corresponds to it directly. But I'm going to develop a little bit further into this to see how we can count the number of nodes and also see the number of nodes, how it's related to the heights of the tree, right? That's also very important because, well, for many algorithms, you want to perform on the binary search tree, for example, let's say searching, insertion, deletion, and also some rotation. It really has to do with the heights of the tree, all right? Hey guys, please, all right? All right, so we talk about here, that's about the depth, and also we can divide that into different levels, okay? Just remember, depth is for the node, height is for the tree. And then we did 2 examples over here. So whenever you want to calculate the height of a tree, you want to start with what's the root of that particular tree. For example, here the root is David. In that case, the height will be the maximum depth, which will be here, 3. On the other hand, if I'm focusing on this particular subtree, where the root is actually Elsa, right? In this case, the maximum depth for the children will be right here, which will be 1. Right? Just to be careful about what the root is for the tree that we're calculating for the heights. Okay, it's very important context information. Okay. All right, any questions from last time? All right, so today we're going to dive a little bit more into mathematical properties for the trees. Okay. So the first thing I want to quickly review and derive together with you. So we spoke about arithmetic sequence last time and see how to calculate its sum. And that one there is simply just quadratic, right? N squared, right? That's the ultimate conclusion you can remember. But now we got something slightly trickier, right? Especially if you want to calculate, let's say, how many nodes you actually got in the binary tree. Of course, in the binary tree, you got some very special pattern there because every node can only branch out up to 2 nodes. That's so the maximum will be 2 nodes branching out. So we want to see exactly how many nodes there are given certain heights. That's something we want to review. Okay? So let's start with the basic. Okay? So we're going to talk about what a geometrical sequence is and how to calculate its sum. Okay? The formula itself, you can memorize it. That's okay, maybe for this course. But I would suggest maybe you can simply try to see if you can just derive it. Of course, when I derive it, I'm going to explain it at the same time. It might take longer. But for you to derive it from scratch, it shouldn't take more than 1 or 2 minutes. So if you really forget about the formula, just make sure you can also derive it yourself back. Okay, that would be what I recommend. Let's see example. Okay, geometric sequence. So one example would be, I got 3 plus 6 plus 12 plus 24. All right, so I'm trying to calculate the sum of the sequence number. And the number is 3, 6, 12, and 24. Okay? And this is geometrical sequence because if you try to see how each number is, how each adjacent pair of adjacent numbers is related, from 3 to 6, you can see it's multiplied by 2. Also from 6 to 12, also multiplied by 2. Also from 12 to 24, also multiplied by 2. Right? That's obvious. Of course, depending on this pattern, you have to identify by yourself. And the way we call, let's clarify some terminology. So we say that the very first term over here is called, of course, initial term, right? Just I. And there's something called common factor, R. So you can think about the 2 over here is the R in this particular case. Okay? Also, we talk about number of terms. Okay? This will be the most important part you want to get right? If you actually get the number of terms actually wrong, you will get the wrong result when you do the summation. Okay, we'll see how to work it out. Let's say for this one, of course, you can see it's 4 terms. It's obvious. You can see that explicitly. But let's see the pattern over here to help you understand a little bit better before we generalize it. Okay. So what I will do is I'm going to rewrite this entire sequence here into something slightly different, but it will still be the equivalent sequence. Okay. I can say 3 multiply 2 to the power of 0. Okay? And then 3 times 2 to the power of 1. And 3 times 2 to the power of 2. And 3 times 2 to the power of 3. Right? And then I'm trying to add them up together. Right? So the correspondence you can see here. This is my initial term, I. And you can see here the 2 right here, to the base, and the 2 here, and the 2 over here, right? You can see these are just the common factor. And then 0, 1, 2, 3, they're simply exponent. That can tell you actually which term we are, right? So now how many terms do we have? So you can see the k here. So k would just be the size of the interval. So we go from 0 all the way to 3 consecutively, right? So you go from 0 to 3, so that will just be 4. Okay, we got 4 terms. Of course, just confirms we got indeed 4 terms over here. But we had to generalize it to really see the formula. Okay? So that's okay? Right? See the formula. So now let's see the more general pattern. Okay? So we have the summation of k terms. So k here is the number of terms we have, all right? So this k over here, of course, will be the number of terms in the geometrical sequence. And then, let's see, we have the first term is simply initial term, I, plus I times r plus I times r squared, okay, plus I times, guys, please, right? When you talk, everybody can hear, including myself, okay? Please. All right, and then I times r to the power of 3, okay, all the way to, okay, I times r to the power of what? So here's something we want to figure out. Given that we got k terms, right? K minus 1, yeah, that's pretty right. Yeah, right. The way to see that is, if you see that here, this is I times r to the power of 0, right? And then you got 0, 1, all the way to some number, which will make up k terms. You're basically saying, I got some interval starting from 0 to what? That is going to give me k. Of course, it's going to be k minus 1. Right? So we just play with the formula interval a little bit. All right, so we start with that. And let me just move this aside, okay, right here. How do we figure out the sum of this sequence over here? There's a little trick. I think this might be the only little detail you have to somehow memorize. That's the only thing I've memorized. Everything else can be derived, okay? So what I do is, I'm going to multiply the sum I'm looking for by another common factor, all right? Let's see how that's going to work. What's going to happen is, I'm going to say r times sk. What's going to be the first term in this new, on the right-hand side? First term. Anybody? First term? If I multiply the whole thing by r, the first term will be r times I, right? Which really corresponds to the second term. So the first term in the new right-hand side here corresponds to the second term, right? So what we have is, okay, I'm going to write down. So the first term will be I times r, okay? So you can think about, let me do a little bit right here. So when I go from here to here, I really just multiply by r, right? Multiply by r. And then for the second one here, if I try to multiply by r, I should get I times R squared, right? Etc. Right? You can see the corresponding. I kind of shift everything to the right by one position, right? And then plus I times R to the 3, and you can also see the correspondence right here quite easily, right? Okay. Let me just make sure I'm consistent with the notation here. All right, let's just finish the sequence. So you're gonna plus all the way. This one here remains to be of size k. We didn't change the length of the sequence, right? We just multiply every term by r. So that means over here you got also I times r. So what will be the last term? I got one more term, right? That will be this one here multiplied by r, which would be I times r to the power of k, right? This would be k minus 1. I just missed that. All right? Follow so far? Right? And you can see that because of the way I'm trying to organize it, this part here is really common between the two sequences. Okay? This part here. What I can do is, why don't I simply subtract one sequence from another? Okay? So what I will do is, I'm going to say right here, if I say r times sk, the second sequence minus the first one, okay? And first of all, I know sk is a common term. So I got r minus 1 times sk. All right? So this is something we can just remember, okay? What I have, right? And if I try to subtract this from this, sorry, I'm subtracting this term here from here. This one completely cancel out. So I got this one minus this, all right? So what I have is, it's going to be I times r to the k minus I, right? And then we can do a little bit more simplification. That one there would be I times r to the k minus 1, right? So now let me also highlight that one there. We're saying this term over here and is equal to this. We want to find out the solution for sk. Well, we can simply divide this one here by this, right? Easy math. So that's the ultimate answer. And then I'll make a little bit of highlights before we move on, okay? So we know that sk will be equal to, right here, okay? So that would be I times r to the k minus 1, which is this term, divided by r minus 1. All right, so that's the ultimate formula. Should you know the formula? Yes. Do you need to know the derivation process I'm showing? Not really. I would say that's optional. But as I said, you don't really want to somehow rely too much on your memory. In the exam, there's no data sheets for you. So just in case you forgot about the formula, this will be your safest bet. Okay? Just memorize just one critical point about multiplying sk by r. That's all I do, right? All right. So why is this formula relevant here? Just very quickly, and then I'm going to move to the next page to elaborate a little bit more. Okay? So here, in our case, we talk about binary search tree, or just binary tree in general. Let's not even talk about search property just yet. Okay? We really want to talk about two things. Initial terms could be simply just one. Oh, let me just write it down more precisely. Okay? So when we say sk is equal to this formula, that will be I times r to the k minus 1 and also r minus 1, right? What about in the case of binary tree? In that case, r here, the common factor will be 2, right? Because every node can have maximum 2 children, right? So that'll be 2. Left and right, basically. And initial term could be if you start counting maybe from the root, which is there's only one root at level 0. Okay, so this will be just 1, which will be the root of the binary tree. And now, this is a tricky bit, right? K. K is really about how many levels are you trying to sum up all together. All right, that's something we'll see. But I can just tell you what this K precisely is, and that's something I will also visualize to you. Okay? It turns out that K here is exactly equal to the height of the tree plus 1. Okay, we have to see why is h plus 1. It's not h, it's also not h minus 1. It's exactly h plus 1. But we're going to see, all right, in a moment. Okay. Any questions about this formula here? It's very fundamental, right? And also, we're going to use this formula tomorrow for the dynamic array as well. So since we covered that already, I can use it directly tomorrow. Okay, let's now talk about the structure of binary tree, right? So what we'll do is, let me write the formula again, right? So put it aside. So we got the sequence over here. So we got I times r to the k minus 1 divided by r minus 1. In the case of the binary tree, what we get is the root 1 node and 2 to the power of h plus 1 and then minus 1. Okay, and then 2 minus 1, right? Just remember r here is 2. And also the k here is h plus 1. We'll see exactly why is h plus 1. Just one moment, okay? And if you simplify it, it's going to be 2 to the h plus 1 minus 1, okay? This is another important formula, all right? But if you already know about the geometrical sequence sum, this one here is not difficult to really derive right away. But we're going to see. But there's a pattern you have to watch out for. Okay? Let's see the pattern for binary tree in general. Okay? So let's now try to, the idea is we try to draw some concrete level, like a level 0, level 1, level 2, and then we generalize it. Pretty much like a mathematical induction. You start with some base cases, and then you generalize it. So we got binary tree structure. Okay, right here. Okay, let's start with the root. So we got the root right here. Oh, let me use a different color. Okay, let's say this is the root of the binary tree. All right, there's only one node, and we say that this is so-called level 0 because if you recall the definition for the depth from last time, so for the root, the depth is simply equal to 0. That means the number of edges from this node to the root itself is 0, right? Just remember the definition, okay? So now I'm going to set it aside some table, okay? Also, we're going to talk about the level something, right? We're going to fill this out number. And we'll talk about the maximum number of nodes at that particular level. At that particular level, okay? Okay, let's observe the pattern first before we try to sum them up. Okay. So for this one here, let me move this guy here a little bit to the left. Okay, right here. Okay. So the one we just did, the root, straightforward. Simply level 0 because the depth is 0. The level number simply corresponds to the depth. Okay. How many nodes do I have maximum for level 0? Just one. Okay, thank you. One here, and for convenience, this is equal to 2 to the power of 0. All right, it's going to be useful, right? And let's do maybe 2 more levels quickly. And if I want to branch out, I can branch out maximum 2 branches right here. Oh, sorry. There's one here. I can do better. Okay, so I got one node here, left, and also right. Okay, and the depth will be 1. That means the number of edges from these 2 nodes to the root, just 1 edge. Just 1 from each one of them, okay? So this will be level 1. And then, number of nodes, 2, right? You got left and right, maximum, which is 2 to the power of 1. Let's do one more, and then we can almost generalize the pattern. Maybe for you, maybe you're doing some similar analysis, maybe just 2 levels will be enough for you, but it depends. I like to do just a few more, just a few at least to observe the pattern. So that means each node there can branch out twice maximum. So I got 1 here, and also 1 here. Also I got 1 here, and also I got 1 here. And the depth will be 2 because, for example, this node here takes 1 and 2 edges to the root. So depth is 2. The level number is also 2. Okay. So now we got 2 here. And the number of nodes will be 1, 2, 3, 4, which just happen to be 2 to the power 2. 2 to the power 2. So now, what pattern have we observed so far? If I simply say, given a particular level, which means every node in that particular level has certain depth in common, am I asking how many nodes maximum can be in that particular level? 2 to the power of that particular depth, right? Okay. That's really the pattern. You want to make sure you kind of feel comfortable, right? So if I just go ... okay? So what we do is, you can think about, so now we can introduce the idea about the heights, because there's got to be some limits, like about how deep a node can be, right? Remember the definition for height of the tree. It will be the maximum depth of the nodes, right? So there's got to be some maximum of the depth. Let's now, hypothetically, let's say we have the nodes that's the deepest right here, somewhere. Okay, let me just move that a little bit. Okay. Let's say this is the node with the maximum depth. So that means when you try to calculate the number of edges, so one here, all the way, right? If you calculate everything, here, all the edges, okay? So the number of edges of the deepest node, right? That will be the height of the tree by definition. So that's h, all right? So let's put h there, and then we can figure out the rest. So that means I can now try to do like this. So now conceptually, you can think about this height of the tree will be h. That means when you try to go from the deepest node all the way up to the root, you have to take h edges. All right? And I can make the tree a little bit more like a tree. Okay. So I can simply try to say that's more like this tree right here, right? It's like a tree. All right, let's now try to see the number of nodes at the last two levels. How about that? The bottom level and also second last level. The bottom level here is here. This will be the bottom level, right? Now, question for you. What should be the level number? We go from 0, 1, 2 all the way to, what's the maximum? Yeah. H, yeah, that's good. That's obvious. Thank you. That'll be h over here. And then maximum number of nodes, 2 to the h, right? And what about the level before? All right. Hopefully you can see the pattern, right? So that one there, 2 to the h minus 1. That one there will be, for example, h minus 1. That means for you to go from the node at this level all the way to the root, it takes h minus 1 edges, right? And that one there will be 2 to the h minus 1, right? And then, right, you can say ... All right, so far we actually really gone through how exactly you can figure out the number of nodes maximum at each level. Now the question is, what's the maximum number of nodes in a particular tree when the height is h? That's the ultimate question, right? So this tree here is really the maximum shape because you can see every level there branches out exactly 2 children, left and right. We have to use some geometrical sequence sum to figure out, right? Okay, let's do that. So what I will do is I'll put in the middle, right here. So the question, the maximum number of nodes in a binary tree given height h. Okay, so we basically sum up these numbers. 2 to the 0, 2 to the 1, 2 to the 2, and then 2 to the h minus 1, 2 to the h, right? Sum them up. It's apparently a geometrical sequence with the common factor 2, right? So what we do is, so 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus all the way to 2 to the h minus 1 plus 2 to the h, right? And what we can do is we can try this particular formula right here. But you actually got different choices, right? You can see here, h plus 1 over here is really the k. If you want to use it directly, that's okay. H plus 1 here is really the k, like a number of terms we have. How many terms do we have in this geometric sequence? H minus 1? Of course, that's critical, right? If you got it wrong, the sequence sum will be wrong. How many terms do we have? Huh? Give me a number. Huh? H plus 1? You think so? Okay. But how exactly do you figure, right? You got 0 here, 1 here, 2 here, h minus 1, h. You're basically asking the size of the interval from 0 to h. So that'll be h plus 1. All right, h plus 1. Okay, so this h plus 1 over here is really the h plus 1 you see right here. All right. So the final answer right here is just going to be 2 to the h plus 1 minus 1. Okay. That's something I kind of said in the beginning already, but I want to show you the derivation process. So the conclusion is, if you're given a binary tree and given some heights h, the maximum number of nodes you might have is this number here. I would recommend don't really memorize it, because I might ask you in different ways in the test or the exam. You want to make sure you're really comfortable with the derivation process. All right? Questions before I move on? Okay, it's a very basic, but I think you guys may have seen that maybe for a long time, so I think it's really nice to really review that quickly, right? Also thoroughly. Okay, so this one's done, and then we're just gonna see, okay, that's the slides. Slide number 6 is the geometrical sequence sum, we did it. And also number 7 is about the level, right? Also geometrical sequence sum. Right, you get the same number. I think just on the iPad it's a little bit more derivation, more visual. Okay, so let's talk about some important properties. I'm just going to focus on 2. I want to look at the relationship between heights and also n, which will be the number of nodes in the tree. Right? Let's look at these 2, okay? Because these 2 are going to impact about any operation or algorithm you want to perform on a binary search tree, which is a binary tree, of course. All right, so let's take a look. All right, so I'm talking about basically slide number 8 and slide number 9. But we have to visualize it just to make it a little bit more easier for you. Okay, let's look at these 2. Okay. But first of all, let's understand why are we studying this mathematical property here. I think that's more important, right? So here we say that if you're given h, so the height h over here is given. Here is given. We want to know what's the corresponding minimum and maximum number of nodes in the tree, right? So if you look at the upper bound and lower bound, so this will be the lower bound, and this will be the upper bound, okay? How do we interpret that? We're basically saying the number of nodes in the tree will be, in the minimum case, linear to the heights. Linear to the heights in the minimum case. On the other hand, in the maximum case, the number of nodes will be exponential on the heights of the tree. Right? That's how you interpret that. And this one here will be exponential to the heights. That'll be the maximum. Okay, maximum, minimum. Let's just visualize it, and then it's actually not too bad. One example, let's say we got the height being 3. That means the maximum depth of the node going from that particular node to the root will be 3 edges maximum, right? So we can visualize it right away. Given that h is equal to 3, so that means at least we have a node like this. Given the root, we got exactly 3 edges to reach that node, right? If you calculate it, you got 1 edge, 2 edges, and 3 edges. So that one tells you h is equal to 3 exactly, right? That's how I can start with. So now, I want to figure out, given that the height is already 3, I want to find the minimum number of nodes. Well, indeed, this is already a minimum. Because, for example, if I want to add one more node, I could. If I simply add one node right here, the heights still remain to be 3. If I add another node here, the height also remains to be 3. But it's not the minimum number of nodes anymore. So the minimum will be just like a completely slanted tree like this. Right? That's a minimum case. All right, so in general, you can think about this. Let's say we have, we got a root, and we got all the way to some nodes right here, right? If I tell you that h is the heights, that means when I try to calculate the number of edges from the root all the way to that particular deepest node, I can count h edges. And if I actually got h edge, well, for example, if you got one edge, that means you got 2 nodes. If you got 2 edges, you got 3 nodes. So the number of nodes is exactly 1 more than the number of edges, right? So that means you got h plus 1 nodes. So that's the h plus 1 you saw as a minimum in general. You guys okay with it? Okay, right. Yeah, please let me know if I'm going too slow, too fast. Well, too fast, I can definitely slow down. If not, too fast, then I'll just move on, okay? Okay, how about maximum? It'll be a completely different concern, okay? Let's still start with that. Given that height is 3, I still got this slant, 2 and 3, okay? So now I got exactly h equal to 3. But without changing the heights, I want to get as many nodes as possible, right? So what I would do is I'm just going to branch out at every level of every node. In that way, I'm just going to get over here and then over here, right? If you do that, this guy here, 2 to the h minus 1, should look familiar to you, right? That's exactly the formula we did right here, right? So let's verify that. So it should be 2 to the, that should be 2 to the h plus 1 minus 1. In this case, it will be 3 plus 1 because we got height being equal to 3, and then minus 1, okay? 15. You can verify, okay? And then what about in general? In general, actually, I'll just visualize it quickly. In general, basically, if you got a tree with one node over here, and then you got exactly 2 to the h, that's basically just a diagram I drew in the previous page. If I got heights will be h, and it would just be 2 to the h plus 1 minus 1. And derivation is right here, the whole page. Right? I basically talked about that in the previous page already. Right? So for the generalization. Okay, you can see the previous page. All right, question. Okay, so this bounds over here is saying given heights, we want to figure out nodes. Let's talk about symmetric direction. Given the node, given n, what will be the heights? Okay, let's see. All right, so this will be the final property we want to see, okay? So this one here, so we are saying that given n nodes, we want to know what's the corresponding minimum and maximum heights. And the heights over here is actually very, very important, okay? The height here is actually going to impact, it's going to be inferential on binary tree or binary search tree operations. Okay, for example, in searching, insertion, deletion, and also rotation, as we'll see later. All right, so these are the operations that's going to be impacted for their performance by the height of the tree. So minimum will be just log, which would be great. And by the way, the log here simply corresponds to when you try to do a binary search on the sorted array, somehow you can see that it's actually also corresponds to that case. I'll visualize it a little bit later. Okay, the best case will be just log. However, if you got we said very unbalanced tree, in that way, searching through it is going to be linear. Okay, you can think about, for example, worst case, searching through a binary search is linear. On the other hand, if you look at the log here, I'll talk a little bit more about how you can derive it. It's actually also very easy. Okay, so this one tells you the best case, or most efficient case. The best case searching is log n. Okay, let's see exactly how. Okay, so once since we already saw the other case about bounding the heights, so this will be very similar. Okay, the principle goes like this. Okay, I'll write down the principle very quickly here, and you can double check yourself. Okay, I'll write down the principle right here. So the case, when you say given the heights, you want to figure out what's the maximum number of nodes. It simply corresponds to, given the number of nodes, you want to figure out what's the minimum heights. So these two cases, one from here and the other one from here, they really correspond to the same kind of tree. So when you got a minimum height, you also get a maximum nodes at the same time, right? So that's something you can also try to convince yourself when you study more carefully, okay? So let's see. If I got the number of nodes being 7, basically I know I want to get a minimum height, so I want to branch out as much as I can so I don't really reach to the bottom that soon, right? If you see what I mean, okay? So let's see here. So I got this node here, so far 1. And then if I go like 2 and 3, I'm actually reaching deeper too soon. I want to get slowed down as much as possible. So I can simply say 1, 2, 3, right? So far the height is only 1 rather than 2. And then 2, 3, and then 4 and 5, and then 6 and 7. That's really the way to really branch out the slowest. You got the minimum heights, right? So the height will be just 2. And let's verify the math very quickly, right? So the height here is simply just 2. And really correspond to the log 1, 2, 3, 4, 5, 6, 7. 7 nodes plus 1. And then once you take the log, minus 1. Log 8, 3. 3 minus 1, 2, right? I'm just trying to show you that the formula works, okay? However, how do we derive it? Okay, I'll get there. Okay, just give me one moment. Let's figure out the maximum height very quickly, okay? The maximum height will be the opposite. If you actually got 7 nodes to spare, you want to reach out to the bottom level as quickly as possible, right? In that way, well, I have no choice. Branch out, branch out, branch out, branch out. 1, 2, 3, 4, 5, 6, and 7. Let me draw better. 1, 2, 3, 4, 5, 6, and 7. If I got 7 nodes, 1, 2, 3, 4, 5, 6, 7. How many edges are there in between? 7 minus 1, right? Just remember that little relation, right? So height will be 7 minus 1, which will be 6, okay? So in general, if you have all the way to the bottom n nodes, that means you got exactly n minus 1 edges. That's what you see over here. All right, let's now just spend just 1 or 2 minutes on how to derive the formula on the lower bound very quickly, and then we'll take a break, okay? How do we get exactly log n right here? Oh, we're making some assumption, by the way. I want to write it down as well. You might be wondering. So the n here, we assume that log of n plus 1 is some integer. Otherwise, you will need to take the ceiling of the number. Okay, but that's something just like a special case. But for the property, we just make it a bit simpler. Okay, let's now derive the formula very quickly. Right? Very easy. So here we are saying that if we got this particular binary tree, and we said that the tree is completely full. So we got the maximum number of nodes, at the same time the minimum heights. Okay? So here the heights is actually h. And then we know that here from before n will be 2 to the h plus 1 minus 1. Right? Maximum. That's what we know from before. Let's now play with that a little bit by moving around the terms, and then we should get it. Okay? So n equals 2 to the h plus 1 minus 1. Okay? So let's move the 1 to the left. n plus 1 will be equal to 2 to the h plus 1. Right? And then how can we somehow get rid of the base 2? You take log, right? So over here, I can say log base 2 n plus 1 equals h plus 1. Of course, with the assumption that n plus 1, take log will give you an integer number. All right, and then so that means the h would be just the log n plus 1 and then minus 1. So that's exactly what you just saw right here. All right. All right, any questions about this? But approximately, you can just think about just log in. All right, if no question there, I think it's nice timing to take a short break, and then we'll do some other concept review. Okay, why don't we take a short break for now? So we're now going to slide number 10. That one just about reviewing the tree traversal algorithm, which I'm just going to do one of them. I will do another one maybe tomorrow in the tutorial to see how you can do Java code for that. So there are basically 3 traversal algorithms. You can do, this will be the purpose. Basically, tree traversal, graph traversal as we do, you just want to systematically visit every object in the collection, which can be a tree or a graph, and then you want to accumulate and do something, right? That's really the common purpose whenever you want to do traversal on some data structure. Right? Just a general thing, you can take a look. And we got 3 types. I'm pretty sure you guys have seen that before in 2101. We got pre-order, we got post-order, we got in-order, right? So this is really the principle you have to know, review, okay? So for example, for pre-order, this is more like an algorithm for like a general tree where the number of nodes, like a child nodes, can be arbitrary. But in our case, we are more focusing on maybe just a binary tree. But for the example I'm going to do, it's more like a general tree, but it doesn't matter, okay? So we're going to review pre-order only today. I'll leave this exercise for you to do in order and post-order as well. And for in order, of course, the precondition is it's only applicable to binary tree. You cannot do in order traversal on a general tree. You just cannot, right? All right, I'll let you guys maybe review the recursive definition for pre-order, post-order, in order, okay? And then we're just going to do one example, okay, for pre-order, just one. So we can take the same family tree over here. It's not binary, but it's okay. Pre-order definitely applies to any general tree, okay? And something I want to just mention as a look ahead. So the pre-order traversal here that we're doing, it's somehow not exactly the same, but it's comparable. To the depth first search that we're going to do later on the graph. Okay, I'll revisit this point again, but I want to make sure you have a notes over here. So if we revisit this later for the exam or for the test, you know right away. It's related to depth first search. Not exactly the same, but similar. Okay. For post order, nothing comparable. Okay, so just want to make sure you get the point. All right, how do we do pre-order? It's recursive, and the procedure goes like this. You're going to visit the parent first, and then you're going to recursively pre-order the first child, and recursively pre-order traverse the second child, and etc. All right, let's start with the top level, okay? So I'm going to visit the root. So let's say I start from just David right here. So that's the root. So I'm going to have David. That's the root. And then I'm going to recursively pre-order traverse the left child. Not left child, sorry, the first child, because it's general tree. Right? So you can think about this part over here is going to be the pre-order traversal of Ernesto. Right? Ernesto here. And this part here is going to be the result for recursively do pre-order traversal on the root of the second subtree, which will be quiz. So that's good, right? That's the big picture, right? Of course, if you want to compute this at the runtime, the pre-order for Ernesto is going to be done first, followed by the pre-order on quiz. But luckily, when you do pre-order on this, it's a single node, like a single node subtree. So the tree itself is the answer, right? So that one there, you can simply say Ernesto. Okay, so that one is done. Okay, you can think about this tree here is done. And then we move on to doing the pre-order traversal, let's say, for this subtree right here. And similar, for that one there, the root is going to be visited first. So it's going to be quiz, followed by the pre-order traversal and pre-order traversal. And for that one there, you can see we got, this is the first subtree. And this is the second subtree. Right? So you can think about this will be the pre-order on Elsa. And this will be the pre-order on Anna. And if I want to do pre-order on Elsa over here, again, Elsa first, because that's the parents. And then pre-order Shirley, Vanessa, and Peter. But they are the base cases individually. Right? So that one there will be just like this. So it's going to be Elsa, just followed by pre-order Shirley, pre-order Vanessa subtree, and also pre-order Peter. Right? Individually, just base cases. Okay? So it's going to be 1, 2, and 3. So Shirley, Vanessa, and also Peter. Right? You can think about pre-order of Shirley, it's just Shirley. Pre-order of Vanessa, just Vanessa. Pre-order of Peter, it just gives you Peter. Right? Finally, I'm done with this. How about pre-order on Anna? Just Anna, right? So the ultimate pre-order you will have is David, Ernesto, Chris, Elsa, Shirley, Vanessa, Peter, followed by Anna. That's the sequence. But you ought to also be very careful about exactly how the correspondence can be shown. Especially, you can think about this here is non-linear. This order here is linear. So we say that whenever you're doing some traversal, you're basically linearizing the nonlinear data structure, right, in a different way. You can linearize using pre-order, post-order, in order, right? So going from here to here, we are basically linearized. Linearized. Okay. Important term. Okay. And I'll leave the post order as an exercise for you. Okay. You can give it a try. You can try the similar like analysis. We have to revisit this kind of a pattern here again to see the sorting property for a binary search tree. We're going to do it again. Okay. A little bit later today. Okay. This one here, exercise. Okay. And then more exercises for you, right? So given this particular, it's really indeed a binary tree. So you can definitely do in order. Let's say given the same tree, figure out the pre-order, in order, post-order. Okay? I'll also give you a solution when I post the notes. Right? Important for you to try. Okay? Are you guys okay about this, right? We don't need to, I think I'll just give you one, just as a quick review. All right? And let's now move on to binary search tree. Okay? Once we finish talking about binary search today, which I'm hoping to get most part done, and then starting from next Monday, we can quickly talk about balance property, and then we can move on to rotation, right? Everything is important. That's why I'm paving the way, okay? Okay, binary search tree. It will be slide number 15 to 17, okay? Oh, there's actually more example here. You can see in the slide, we also got pre-order right here, and also post-order, and also in order. All right, you guys can take a look too. Okay. Okay, slide number 15 will be about binary search tree. Okay, you can take a look at binary search tree definition. I'll go over that very quickly, and also for our implementation for the binary search tree, we ought to distinguish between internal nodes and also external nodes. I will visually clarify very quickly today, but I will do a little bit more in the tutorial, hopefully tomorrow. If no, definitely the tutorial next week, right? That's something you also need to be clear, because the binary search tree template you'll be given in the programming test and the assignment will be the same. We follow the same convention. So you definitely need to know that detail, okay? And sorting property, right? That's something we'll need to review too. Okay, let's now talk about binary search tree, sorting property. Let's review quickly about binary search tree, the definition, right? So given this root over here, and usually for every node in the binary search tree, we should really store the key and also the value, right? It's more like a pair, like an entry. So you can think about the key value pair is set to be an entry. And then we say that the key over here is for searching purpose. And it's really for, since it's for searching purpose, it should be unique. There should be no duplicates, right? But for the value, as many duplicates as you need it. It's a recursive property. Given any root, I'll talk about it. Given any root over here, every node on the left subtree must have their key value strictly less than this value. And every node, their key on the, every node in the right subtree also have their key value larger than that, right? That's what you have seen in the 2101. Let's verify that right away. Let's say, for example, if I look at this root, and then I can see that the left subtree over here, and also the right subtree right here, right? You can see every node here, you can double check, every node here is strictly smaller than 44. Every node here on the right subtree is strictly larger than the root. And because it's recursive, I can go further. Once I'm okay with this particular node here, let's go down. And then I will choose, let's say 17 over here. As far as 17 is concerned, being the root, this will be the left subtree. And this will be the right subtree. And let's now double check it again. You can see every node in this subtree, which is 8, less than 17. Every node in this right subtree here for 17, these numbers are strictly larger than 17, right? And etc. You have to make sure this kind of check is actually done for every node in the tree. Of course, you can do it either iteratively or recursively, but usually recursively. All right, so that's a very important property. That's called the search property, which you will see on the slides. Okay, so this is so-called a search property. If the search property is satisfied, that means you have a binary search tree. All right. And there's another property called sorting property. So once you have a binary search tree, there's also a so-called a sorting property. What does that mean? Sorting property goes like this. Given a binary search tree, which is nonlinear, if I try to linearize it using the in-order traversal, what would I get? Of course, I'll get a sequence. But what is so special about that sequence? I like that. I know what you mean, but can you say ascending order? Okay, I like it. It's sorted in the ascending order. That's good. Awesome. All right. In-order traversal is going to give you a sorted key sequence in ascending order. All right, so that's also a very important property. Let's just sketch it down a little bit, okay? So let's quickly summarize. So given a binary tree that happens to be a binary search tree. Number one, you have to check for search property, which we just said, search property, which means it can be done recursively. And also, you have the sorting property, in which case you have to perform in-order traversal. Okay, IoT in-order traversal. Okay. And let's say this. Given this tree here, let's say the root over here is parent P. And then here you got your left child, and over here you have your right child. Okay, let me just change the color over here. Give me a moment. So this one here would be parents. All right. So now, given these three reference points, okay, let's see what we have. So what we have is, if you somehow do in-order traversal, you know that you're actually going to generate some linearization, like a sequence right here. So this part here is going to be the in-order, oh, actually I can just write here. This part here is going to be the in-order traversal of the left child. That one there is going to give you a sorted sequence, right? That one there is going to give you a sorted sequence where every key is less than the key of the parent P. Okay, so now let me put this one in the middle, right? So that will be the key of the parents. Right? In order is we try to do in order traversal on the left subtree. That one there is going to give me a sequence where it's sorted, and also every node there has the key strictly less than key. So you really have to consider both the search property as well, right? And after that, we also got the right-hand side. That will be the in order traversal from the right child. So this will be the sorted sequence where every key over there is strictly larger than the key of the parents. Okay, so that'll be the in-order traversal of the right child right here. All right. By the way, so if you look at saying we have something in the middle, and then we got these two somehow being sorted, and also everything is less than, everything is larger than. It looks familiar, right? Which sorting algorithm works in a very similar way? Yeah, go ahead. Sorting, not searching. Yeah. Good try, but. Okay, let me rephrase my question again. Actually, that's nice because we wouldn't cover that particular sorting algorithm actually in very much detail. Let me say that again. If you try to linearize this particular binary search tree, you look at somewhere in the middle, which will be the key of the root, and then you have some sorted sequence generated from the in-order traversal on the left child. And here, the sorted sequence generated by doing in-order traversal on the right child. Also, at the same time, because of the search property, every key here is strictly less than this. Every key here is strictly larger than that. This kind of an organization is actually very similar to one of the sorting algorithms. Selection sort? Insertion sort? Heap sort? Quick sort, yeah, quick sort. Because think about P there is like a pivot, right? And then left-hand side, right-hand side there, just something strictly larger than, strictly less than, right? There's some connection you can think about, all right? I'm not really suggesting you can do a quick sort by binary search tree. That's not what I'm saying. I'm just saying make some connection there, right? Don't get yourself confused, please, okay? All right, any other questions about this? Okay. I got about 12 minutes. I think we can do some very quick observation. Okay, I think we're pretty good. Okay. So number one, a good exercise for you. How about this? Why don't you take this tree over here and do in-order traversal? Another way to really double check if a binary tree given is a binary search tree is simply do in-order traversal. If the sequence is sorted, then of course it's a binary search tree. Why don't you do that very quickly, and then I'll show you what I want to do. I want to show you some correspondence, which would be very, very useful when we talk about insertion and deletion of binary search tree. Okay? Everything has a reason. Yeah, take a moment, right? Shouldn't take you too long. In order traversal. Okay, everybody has a tree, so I'm gonna put something on my iPad as well. Okay, let's take about 30 seconds or so. I'll write it down. Order traversal. All right, I'm done. But that's not fair because I got a solution on my notes, so I just copy it, right? But it shouldn't take you too long, right? I hope, right? All right, done, okay? Do you mind telling me what the answer is? Left to right, please. Yeah? Yeah? Uh-huh. Yeah? Yeah? Uh-huh. Yeah? Uh-huh. Yeah? 80, and then? Uh-huh. Oh, after 82, are you sure it's 93? You're missing one. Okay, good. No worries. Okay. And then after 82, you got 88, and then 93, 97, right? Very good. Just be careful. Okay. All right. That's a sorted sequence, right? Sorted is a binary search tree. Good. Let's now see some correspondence quickly, okay, to make my point. Let's now start with the 44 we have. That's the root. 44, the root. 44 right here. Oh, again, let me just make the point again. So this is the nonlinear structure. And the in-order traversal, of course, is trying to create a linearized version of the components. Okay, linearized version. And if you look at, for example, this left subtree over here, and also you look at this right subtree right here. Not surprising, the orange one here is corresponding to this sequence right here. And the right subtree is linearized into this particular sequence. You can double check, right? Let's go a little bit deeper, right? Wouldn't take long. And then if I try to look at, for example, 17 right here. That one there, of course, I got my 8 right here. Also, I got these nodes right here, right subtree, which will be corresponding to right here. Okay? And symmetrically, I can also do, let's say, given 88, which is right here. And then I can now do this one over here, left subtree, and also right subtree. Okay? You can see left subtree over here, and also right subtree over here. And then you can feel free to go a little bit deeper, right, to see how you can get down to the base cases. What will be the base cases? Base cases will be a subtree with just the root itself. So a binary search tree with only one node. Oh, sorry, a binary, I'll write it down here. Base case. Base case. A binary tree with just one node is automatically a binary search tree because the node itself, the key, just sorted. Right? It's like a one-element array is sorted automatically. Okay, and you can, I will just do quickly. So you got 8, 21, 29, 54, 80, 93. 8, 21, 29, 54, and also 80, also 93. So these are the one node subtree you have. You might be wondering about the square, right? That's something, let me explain them maybe when I get to the code tomorrow in the tutorial. For now, just ignore them, just for now, okay? Okay, let's talk about something else, okay? Also still relevant. Right here. You have in order traversal, right? That's something we did just earlier, just a few seconds ago. So now here's my question to you. Let me pick one node from the tree. Let's say I pick this node. Here's my question. What key value can be replaced for this node? Meaning that if I want to replace the 76 by other value, tell me the exact range of the values. Try not to look at a linear sequence. In that way, it's very obvious. But if you look at it, try to look at a tree, because that's the main thing I want to show to you, right? I want to kind of use this one here to tell you about the predecessor and successor, for in-order traversal, but we'll get there. If I want to replace 76 by some element, what will be the legitimate value I can replace that for? What? For example, can I replace it by 82? Oh, sorry, not 82. 82 is duplicate, right? Let me just say that again. Can I replace it by 84? Doesn't seem like, because 84 is actually already larger than 82, the parent, right? Can I replace it by, for example, maybe 79? Looks possible, right? Right? But I'm just guessing, right? But I want some precise range. Can anybody give me the range? I want the range of key values I can use to replace for the 76 at this point. I like your answer, but it's not concrete enough. I want the values. From 66 to 79, okay, I like the answer. Okay, that's correct answer. But how do we see that, right? Okay, let's see. Okay, let's now try to look at the corresponding in-order traversal. Okay, let's say here, 76 is right here. And then if you look at the sequence itself, remember we talked about predecessor, successor, right? This guy here is the predecessor. And this one here is the successor. In the sequence, you can simply see if I want to replace this one here by some value, it has to be larger than 65 but less than 80, right? So the correct answer should be, first of all, so this one can be anything between larger than 65, but gotta be strictly less than 80. So that will be the range of values. Okay, that's one thing. But I think the more important thing is to see these two values, because in the linearized sequence, it's very easy, left and right. In the tree, not necessarily, right? The predecessor, 65, is actually right here. Seems to be some kind of like an ancestor, right? You gotta follow the parent link. On the other hand, you can see the 80 is just happen to be the right child, but may not be, I can tell you. May not be the right child right away. Could be something else. All right? So what you want to convince yourself is, whenever you're given some particular node right here, you want to be able to figure out its predecessor and successor in the in-order traversal. Imagine that if I want to do in-order traversal, I will do, for example, 54, and then I do 65, and now I want to do the right subtree. In that right subtree, I have to do 82, and then I do the left subtree, which will be here. And then for that one there, there's nothing here. So I got to do 76. And then I do the right subtree, and then I do 80. You want to kind of follow that order to see exactly where the predecessor and successor is. Right? That's my point. Okay. So this is the predecessor. And that one there is the successor. Okay, that's my point. Okay, and one exercise for you. Okay, I'll write it down and then I'll let you figure out. So now here's a question. Let me pick this node. Let's say this one over here. Okay. So this one here, for example, what can we replace it with? And number two, can we replace it by 83? Okay, two questions, very simple. Exercise for you. Okay. Got about, I think that's good. Okay. All right, I think I'll stop here. And then tomorrow tutorial, we're going to do a little bit of Java coding. But before that, I'll do dynamic array. So please make sure you go over constant increments from last week's tutorial. It will make it a little bit smoother for you. All right, I'll see you tomorrow. Okay.